Hello again and welcome to lesson 2 on probability. Right, this one is focusing on formulae, and there are two key ones that we need to know for S1. The addition rule, which we'll do first, and the multiplication rule, which applies to conditional probability. So, to prove the addition rule, this links the union of two events and the intersection. And we're going to use this Venn diagram to do so. So we'll use little a and little b to represent the probabilities of events A and B, and we'll represent the intersection with the letter I. And that means we can put an I there on the diagram. I hope you're happy with that. And if you consider this region, well, the whole of A is little a. So this bit here must be little a minus the intersection. And in the same way, we can write that this area is little b minus I. So if we want the union of A and B, that's everything within A or B or the overlap, we add together those three regions. So A minus I is the first region, I is the second region, and B minus I is the third one. And we'll see that when we tidy that up, we're left with A plus B minus I. So if we replace those with what those little letters represent in the formal notation, A is the probability of A, B is the probability of B, and I is the intersection, and we have our formula, the addition rule. So let's have a look at how we can use that rule. We have an example here where we know the probability of A and B, the two events happening, and we know the union. The first thing we want to find, part A, is the intersection of A and B. Well, that's a straightforward application of the rule that you have just written down. So write down the rule, substitute in the known values, those three numbers there. The only thing we don't know is the probability of the intersection of A and B. And a little bit of rearranging, add that over from right to left and subtract 0.9, and we can quite easily work out that the probability of the intersection of A and B is 0.4. So part B, this is even easier, quite trivial really. The probability of not A is always 1 minus the probability of A. There are other ways to work it out, but if you know the probability of A, that's by far the quickest. So subtract 0.6 from 1 and you get 0.4. Part C, well, the easiest way to work this out is to draw a Venn diagram. And if you're not sure what to do in most questions, a Venn diagram can be very helpful. So in my Venn diagram, the first thing that I can label is the intersection, and we worked that out in part A. So I can label 0.4 in the middle, and I'll fill in all the other parts of my Venn diagram by subtraction. So that bit there is 0.2, because the whole of that region for A, probability of A is 0.6, so I subtract the intersection and get 0.2. And similarly for B, I get 0.3 by subtracting the intersection from the probability of B, which is 0.7. And we fill in the last bit by subtracting everything else from 1. So what I want is the probability of not A union B. So let's just consider for a moment what that means. That means either A does not occur, so not A, or B occurs, or both. So A does not occur and or B does occur. Now this bit, at the end of this bit, I want you to pause the video and just check that you agree that these three numbers, these three regions, all satisfy that criteria: 0.3, 0.1 and 0.4. And if you're not sure why, ask me in class. Okay, but that adds up to 0.8. Right, part D. Well, it says to do this two ways, and we're going to do it two ways. Method 1 is to use the addition rule. So if we write down the version of the addition rule for this situation, the probability of not A union B is the probability of not A plus the probability of B minus the probability of the intersection of not A with B. And, well, we know that. Stick that in. We know that. And we know that as well. So there's only one bit here that we don't know, and that's the bit that we're trying to find out for this part of the question. So again, we just have to rearrange this slightly. Subtract 0.8, add the probability of not A given B, and satisfy yourself that it rearranges to give this which simplifies to 0.3. Now there's another way to do it, otherwise I wouldn't have asked you to do it two ways. Method 2 is to use the Venn diagram. And, well, it's actually trivial from the Venn diagram. Okay, we want the probability of not A intersection B. So that's the bit where A doesn't occur and B does. So look on the diagram. It's got to be inside the circle for B, but outside the circle for A. And that must be 0.3. Happy days. Now we come to the second of our rules, the multiplication rule. Very important, it deals with conditional probability. So this is when you know something about the outcome of an event, and that changes the probabilities of what will actually have happened. So for example, if I know that I've rolled an even number, I don't know which one, but I know I've rolled an even number on my dice, then that changes the probability of me having rolled a prime. Okay, because it's narrowed it down. It's reduced the possibilities already. And we have a mathematical rule for that, which we're going to look at now. So if I consider the probability of event A, if I know that event A has happened, then I'm somewhere in the shaded region, okay, on my diagram. So what is the probability of B given that, knowing that I'm in this region? Well, it must be, what's the likelihood of me being in that region that has now got red in it? Okay, so it's like I've got a reduced sample space, which is just the circle for A. And I want to know what is the probability that I'm within the red bit. Okay, so I need the red bit divided by the whole of the probability of A. So in notation form, that would be the probability of A intersection B divided by the probability of A. Okay, so that gives me the multiplication rule. If I just multiply by the probability of A to rearrange that, I get it in this form here. The probability of A intersection B is the probability of B given A, and that's the vocabulary we need to use, multiplied by the probability of A. And you'll see how useful this is when we start to use it now. So, spinners. Don't they just love spinners? We've got 4 possibilities on each of these spinners. They're equally likely. So again, a bit like we've done already, we're going to draw a sample space. So we've seen how this goes in the previous lesson. 2 spinners, each one has an axis, and we put the possibilities on 1, 2, 3, 4 for each. And when we fill in the grid for the sum, that gives us 16 equally likely outcomes. That's our sample space. Now method 1 for doing this is called a shrunken sample space. Okay, and that's because given that at least one spinner lands on a 3, well, we're told that one spinner has landed on a 3, so we're not picking from these 16 anymore, we're picking from these 7 outcomes that I've circled. Okay, they're the only ones where they include at least 1 3. So these reduced possibilities, reduced number of outcomes, that's my shrunken sample space. So we're now picking out of 7, not 16. So we need to know how many ways to get exactly 5 out of these 7. And I've circled them. It's easy to spot. There are 2 ways to get exactly 5. So out of my 7 equally likely outcomes, there are 2 ways to get exactly 5. The probability sort of jumps out at you there. So the probability of getting a sum of 5, given that there's at least 1 3, is simply equal to the 2 divided by the 7. Now the other method is to use the formula that we've just looked at, okay, for conditional probability. And that tells me that the probability of getting a sum of 5, given that at least 1 3 has occurred, is the probability of getting a 5 and at least 1 3, that's the intersection, divided by the probability of getting at least 1 3. And it's easy to see that the probability of getting a 5 and at least 1 3, well, that's those 2 that are in a box, so 2 out of 16. And the probability of getting at least 1 3, well, there's 7 ways to do that, so 7 out of 16, and that simplifies to 2 7ths, just like before. Okay, on to our next example, and we see here the first thing we want to find is a conditional probability of D given C. So we want to find the intersection because if you need a Venn diagram or if you want conditional probability, you need to know the intersection. And so for that, we use the multiplication rule. So write that out. The probability of C intersection D is equal to the probability of C given D multiplied by the probability of D. So note this is one version of the multiplication rule. It can be written as a fraction, which we'll see later on. So if we put the values in there, it's fairly straightforward. From the values that we're given, get 0.18 is the intersection, and that means that we can draw a Venn diagram. So if we go ahead and do that, straight away we can put 0.18 in for the intersection, and the rest of the diagram, as before, we work out by subtraction. So the probability of C is 0.2, so if we subtract the intersection from that, we get 0.02, and that gives us that region. The probability of D is 0.6, so subtract the intersection from that, we get 0.42, and subtract all those three numbers from 1, and it gives us 0.38 for the region around the outside. So part A, it wants the probability of D given C, so this is straightforward using the multiplication rule. In its other form, so this is the fractional form, you need to be familiar with both. So the intersection of D and C divided by the probability of C, and it comes to 0.9. Now if you look at part B, the intersection of not C with not D, and to do this just think about what it means. So not C means that C doesn't occur, and not D means that D doesn't occur either. So the only bit of the diagram that corresponds to is 0.38. So we can do that straight away from the Venn diagram with no more working required. Part C is similar, intersection of not C with D. So C doesn't occur and D does occur. Okay, so that's 0.42, the only part that's outside of C but inside of D. Right, you may need to pause and review that at this point. Anyway, this one here, we want to work out a conditional probability again, probability of B given A. So we're going to want to know the intersection and whether we draw a Venn diagram or not. That's how we're going to start. Now this one here, we should notice that we can use the addition rule because we know the union. That can help us get the intersection of A and B. So write out the addition rule. The probability of the intersection is equal to the probability of A plus the probability of B minus the probability of the union. And we know all those bits and pieces, so we can just stick them straight into the formula and just be grateful that we can in this case. So tidy that all up, put it all into tenths. I don't need to tell you that. And anyway, what you get is 2/10 or 1/5. That's the intersection. Okay, why do we need that? It's so that we can use the formula. We can use the multiplication rule for B given A, because that's equal to the intersection of B and A divided by the probability of A. So we use the probability of the intersection we've just worked out, which is 1/5, divided by the probability of A, which we already know, 3/10. And that's quite easy to simplify down to 2/3. So that's part A. Now I could have done that via the Venn diagram. I could have done a Venn diagram before now. I chose not to, but I'm going to use it for part B and possibly part C. So if I draw that up, again, start with which bit? The middle, that's right. So the intersection was 1/5, fill that in, and then go ahead and do all the rest by subtraction. Oh, I've forgotten to label them A and B. Hopefully I'll remember to do that in a minute. So subtract the intersection from the probability of A, that gives you 1/10. Subtract the intersection from the probability of B, that gives you 1/5. Okay, pause it, go through and double check those calculations. And the bit around the outside is simply 1 minus all the other probabilities, and that gives us a half. Okay, so we've got our Venn diagram. What are we going to do with it? Well, we want the probability of B given not A. So B given not A is probability of the intersection of B with not A divided by the probability of not A. And all these bits and pieces we can get from the Venn diagram. So B intersection not A, that is when it's inside the loop for B but outside the loop for A. The probability of not A, that's all the bits that are outside the loop for A. Okay, so there are two bits that are outside the loop for A. Check that they are 1/5 and 1/2. Check you agree with that. In any case, that's what it is. We simplify it down. It's 1/5 divided by 7/10, and that becomes 2/7. And last but by no means least, part C, and it wants you to calculate this rather horrendous looking jumble, which seems a bit random but actually isn't. I want you to have a look at it carefully, try and understand what's going on here, why these two things have been put together. It's quite simple to do because they're four quantities that we already know, two that we knew to start with, two that we've worked out in the previous parts of the question. And when we put it all together, we get 2/5, and this just happens to be the value for the probability of B. Okay, now do you think this is a coincidence? Could be. I think you can guess where this is going. Think about what that link means and ask me about it if you want to know. But that brings us to the end of lesson 2. I hope you enjoyed it. See you in class.